Consider these two overlapping quarter circles inside a 1 by 1 square. What is the area of the shaded region that is not in the overlapping section? To start off, we're going to use a little bit of algebra and geometry. Employing a little bit of symmetry, we're going to cut this problem in half, literally. Taking the lower rectangle, the dimensions of that rectangle are 1 by 1/2. So the area of that rectangle is 1/2. We'll use this a little bit later on. Next, we're going to construct a right triangle inside this rectangle, and to find the dimensions that we're missing on this right triangle, we're going to have to consider the bigger picture. Inside here, we actually have the construction of an equilateral triangle, and if we split that in half, we get a 30, 60, 90 right triangle. The height on that would be the square root of 3 over 2. So now we have this measurement for our right triangle. 1/2 base times height, 1/2 the square root of 3 over 2, times 1/2 is the square root of 3 over 8. So that is the area of that right triangle. Next, we're going to use the area of a sector formula to find this area right here with an angle, which we can tell from the 30, 60, 90 right triangle is an angle of 30 degrees. So the ratio of the area of the sector to the area of the circle that it would be inside of is equal or proportional to the angle theta over 360. Now, since we know that this angle is 30 degrees, we can replace that in our proportion and solve for the area of the sector. 30 over 360 reduces to 1 over 12, and solving for the area of the sector, we get pi over 12. So the area of the sector is pi over 12. That leaves us with finding the area of the shaded region that we're interested in. So taking the area of our rectangle, subtracting off the area of our triangle and the area of our sector, we get 1/2 minus radical 3 over 8 minus pi over 12. But thinking about this, the area that we're really interested in would be double this by symmetry. So the area of the shaded region is 1 minus the square root of 3 over 4 minus pi over 6. Or as a decimal, this would be 0.0433885225. Time to level up and do this problem a second time using a little bit of geometry, that is coordinate geometry, and calculus. So imagine our 1 by 1 square on the coordinate plane, and the two curves that make up the quarter circles are given by f of x and g of x. So here, f of x would be the top quarter of a circle with a radius of r centered at the origin. So by its description, we can write the equation x squared plus y squared equals 1. And solving this equation for y, we get two equations, actually two functions, a top and a bottom to a circle. The positive square root will give us the top of the circle, which is what we're interested in. So f of x is the positive square root of 1 minus x squared. Now g of x is the bottom quarter of a circle of radius 1 as well, but it has a center which is the point hk of 0, 1. So using the formula for a circle, we get the formula for this particular circle to be x squared plus y minus 1 squared equals 1. Now solving this particular equation for y and using the bottom half of the circle that we're interested in, we're going to get g of x to be equal to 1 minus the square root of 1 minus x squared. Now we're ready to employ a little bit of calculus. To find the area that is the shaded region, this is the area between the two curves. Now finding the interval in which we're going to integrate over here, we find the point of intersection here to be radical 3 over 2 comma 1/2. So our interval of integration will be the square root of 3 over 2 to 1. Now we're going to integrate the top curve minus the bottom curve, and here g of x is bigger than f of x on this interval. So when we find the area between the two curves on this interval, we're going to do g of x minus f of x. So to find the area between these two curves, to first find g of x minus f of x, we're going to subtract the two functions. And we're going to get 1 minus 2 square root of 1 minus x squared. Inputting this into our function and looking at our integrand, we can split up this integral into two separate integrals and take it piece by piece. Alright, so let's write out our integral. And first thing we're going to do is split it up and evaluate the first part of this, which is pretty easy to evaluate. So the integral from radical 3 over 2 to 1 of dx is just going to be the difference of these two values. So we'll just write them out explicitly. Next, we're going to try to find the integral that I have highlighted in pink here. That's going to be through a little bit of substitution. So this might be an integral you're familiar with or maybe not. So we're going to do a little substitution here and we're going to do some trigonometry. We're going to let x be the sine of theta, so that would make dx equal to cosine theta d theta. And evaluating what the radical would be here with the substitution, we find that it's just equal to cosine of theta. Pretty nice. So putting the two parts of our integrand together, we get cosine squared d theta. And that's going to be integrated from some new limits of integration since we made a change of values. So if x1 was radical 3 over 2, theta 1 would be pi over 3. And similarly, if x2 was equal to 1, then theta 2 would be pi over 2. So now making that substitution, we have to deal with the integral of cosine squared theta. We're going to use another substitution, this time a trig identity, which is a double angle formula for cosine. And solving this formula for cosine squared, we're going to substitute this in here to make our integrand a little bit easier to deal with. And because of the linearity of integrals, we can also split this one up into two simpler integrals. The first one of which we'll be able to evaluate no problem, and the second one will take a little bit more time. So if we look at that first part of the integral from 1/2 dx from pi over 3 to pi over 2, we're going to find that this value is going to equal pi over 12. Next, we're going to take the integral for cosine of 2 theta and integrate that, which is the sine of 2 theta over 2. And we're going to evaluate that from pi over 3 to pi over 2. Okay, so then we're going to get 1/2 negative square root of 3 over 2, which is negative square root of 3 over 4. Wait a minute here. Let's take a look at this. I think I made an error. Oops, I forgot the 1/2 when I split the integral. So let's just make an adjustment here by multiplying our answer by 1/2. That'll give us negative square root of 3 over 8. All right, that's starting to look a little bit better here. Okay, so we've evaluated our integral here so that we've got now the second part to our equation. To find the shaded region now, we're going to put all of these values together. So 2 times the integral would give us pi over 6 minus square root of 3 over 4. And we're going to put that together with the first part that we had found. And we're going to combine the square root of 3 over 2 with the square root of 3 over 4. And rewrite our terms here. And that'll give us 1 minus pi over 6 minus the square root of 3 over 4. The exact same answer that we got from our first part. The power of calculus at hand. So there you have it. I hope you enjoyed this video and I hope you were able to figure it out. Until next time, please like, subscribe, and hit that notification bell.